Microbiology, those tiny things we have to use a microscope for. Bacteria, this is a huge group, and they're all called prokaryotes because they have no nucleus. It seems like a primitive condition, but these guys are pretty advanced. The archaea, this is an ancient group. They're still around. They oxidize sulfur and do other things for energy. Eubacteria are the ones we're most familiar with. They're the ones that cause disease. They're widespread. Oh, look at the head of a pin coated with bacteria. Whew, creepy. Basic features. Okay, there are so many types of bacteria that we have to look at different features to figure out what they are. We can't just say, hey, this one's red, it must be E. coli. No, we got to look at the cell wall, for example. It's a polysaccharide, meaning it's a carbohydrate. Poly, many sugars. Peptidoglycan is the word. If they have a thick wall, then we call them gram-positive, and I'll talk about that shortly. Another way to identify them is by their shape. If you've ever admired someone's anatomy, you're looking at their shape. So we have Coccus, which is round. You might have two round structures, and we have diplococcus. We think of gonorrhea. Or how about a clump of coccus? We call that staphylococcus, or just staph. Our skin is coated with them, and it's a common source of skin infection. Strep, think of a chain like a pearl necklace of coccus, or just strep, as in strep throat. Bacillus, these are rod-shaped, and we think of anthrax, which is something very dangerous, or streptobacillus. That's a chain of bacilli. Spirillum is or called a spirochete. These are corkscrew shaped, such as syphilis, although lots of harmless bacteria have that shape as well. The way they grow is called their colony morphology. You see, one bacteria you cannot see without a microscope, but when there are millions of them growing together, now they're visible, such as this hand of a child pressed into an agar plate with nutrient material. The bacteria, each type, forms a type of colony. So we can look at that and say, hey, that yellow color and that shape, I think I know what it is. Gram stain, I mentioned the peptidoglycan, that cell wall. When we take a sample, such as blood or urine, we're going to streak it on that agar plate, and then we're going to stain it with crystal violet. And if it picks up that purple stain, then we call it gram-positive, has a thick wall. Or if it doesn't, then we have a thin wall, gram-negative. And this is going to tell us how to treat the patient. We do this by smearing the Petri plate with the suspect organism, and then we place the antibiotic disc there. And the antibiotic that has the biggest halo is the one we're going to use, as long as there's no patient allergy or responsive allergy to that particular drug. If we have a gram-positive bacteria with a thick wall, then we're going to use penicillin. The choice antibiotic for a gram-negative bacteria is the Erythromycin group. Capsule. Think of it, something that's so incredibly slippery, like a watermelon seed you're squeezing in your finger. That is what a capsule is like. It has this slippery surface that can escape our macrophages, those white blood cells in our immune system. So, and these are ones that cause us a lot of infections because we have a hard time controlling them. A good example, Streptococcus pyogenes. It's laying there right at this second in your upper respiratory tract, right, in the back of your throat, and it's dormant until you have a weakened immune system, such as you get chilled, you miss some sleep, you're eating poorly, depressed, whatever it is. Then Streptococcus pyogenes is going to start to divide and penetrate, and we get that telltale sore throat as this organism slips away from our macrophages. So you know what? We can't afford to let our health. We got to sleep, we got to eat right, or Strep pyogenes is going to take us down. Glycocalyx, think of something slimy, the slime layer. It attaches to smooth surfaces, such as the way Strep mutans attaches to the smooth surface of our teeth. There it's going to absorb carbohydrates. You see, it doesn't eat our teeth. It uses the food in our mouth, and then it secretes or urinates acids. It also uses calcium to protect itself, and that's the plaque. And that's why we've got to brush our teeth and floss at least once every 24 hours and do it right. The bristles are soft. You move in a circular pattern. Hold the toothbrush in an angle because you want to wiggle it under the gum line. And here's why. Because there's a periodontal region. Think of perio meaning around. At the junction between the crown and the root, that's where sometimes these bacteria will start to gather. And that's why you got to tilt the toothbrush. Or in time, the gums will swell and you'll have periodontal disease. Gradually, the teeth fall out. And you don't think this is going to happen until one day you're in your 50s or 60s and the tooth start getting a little loose. It's a very gradual disease. Endospores, perhaps the oldest thing on Earth, is a bacterial endospore found in the gut of a mummy. I'm not joking. They're incredibly resistant. You can dry them out. You can boil them. You can freeze them. Alcohol, they laugh at that. Even radiation. They're highly resistant, but they can be killed. But they have to be killed when they're in their vegetative stage. Okay, and I'll talk about that. You see, for a bacteria, they can't just hang out in a endospore stage forever. They have to reproduce. And to reproduce, they enter that vegetative cell stage, and that's when we hit them. So when you have an antibiotic, you can't just take it for 2 or 3 days, because what if some of them bacteria are still in their endospore stage? The medicine's not going to work. And so sometimes people take it 3 days and they go, okay, I'm going to save these pills for the next time I get sick. But they don't realize that there's a few endospores that are going to jump out of their jump into a vegetative stage on day 4 or day 5, and now we got a second infection, and the medicine's not going to work as well, and it's a big problem. Why don't you avoid that one? Toxins. There's different types. Exotoxins. Most toxins are proteins, by the way. These exotoxins tend to affect certain organs of the body. One type of bacteria, Clostridium botulinum, I just call it C. botulinum, produces incredibly powerful toxins that cause flaccid paralysis. And they do this by binding up the synapse between nerves, and they're going to inhibit the release of acetylcholine. Acetylcholine is a natural neurotransmitter we find there, and C. botulinum is going to mess with that, and so we kind of relax to death. Although in small doses, local use can relax muscles and reduce some wrinkles and other things too. Okay, it's used for anal, spasms. It's got wide use. A relative of botulinum is C. tetani. It also messes with acetylcholine by inhibiting, I can't say that word, removal of acetylcholine at the nerve synapse. So it's kind of the opposite of C. botulinum. They're both neurotoxin exotoxins because, remember, their target is the synapse between nerves. C. tetani, we think of that full body tetanus, which is muscular contractions. Usually starts as a localized, like the arms, the jaw, but eventually the lower back muscles will overpower the abdominal muscles, and we get this terrible rictus. Very sad. C. difficile, sometimes called C. diff, is widespread in certain wings of the hospital, especially where there's been some gastrointestinal surgeries. A protein enzyme released by C. diff causes extreme diarrhea, and it's highly contagious. And this is when we glove up, mask up, hook up the HEPA filter, and even put an apron on. Sometimes antibiotics bring on sort of a weakness to this particular bacteria. Endotoxins, a little bit different than exotoxins because they release it when they die. If you look down below, you'll see endotoxin. When bacteria dies, then it emits those toxins. So that's why you have to be careful. You got a patient's really sick, and you give them a massive dose of antibiotics, and suddenly their system's under attack from these toxins, and you get hemorrhaging, and may interfere with blood clot formation as well. Flagella, how do they swim? These are proteins bent like a helix. I think of cholera. Cholera is still throughout the world. It's going to cholera uses its flagella to swim through the mucus coatings of our intestines. And the problem with cholera is it causes intense and chronic diarrhea, and especially in children. And the problem is it's when we have sewage contaminating drinking water, which is never a good situation. And it's, it just keeps popping up. Asia, Africa, Middle East, it's probably around to stay. It's it's even with a vaccine, which I have, I'm still susceptible because there's different strains of this guy. Generation time, interval of time between each bacterial cell division. The champion being Escherichia coli. We often just call them E. coli. 20 minutes between cell divisions. So let's say you eat half your sandwich, leave it on the counter. Later that day, you're looking at over 1 million E. coli. Not a good situation. That's why we have refrigeration and really strict controls and gloves and so forth. Pili. This is a clever way that bacteria anchor themselves and they transfer their genes from one to another. And I think of Neisseria gonorrhea, which has become drug resistant. Gonorrhea is on the rise. You're hearing of more cases these days, and so some researchers are experimenting with these anti-pili antibodies, and so they block gonorrhea from using their pili to reproduce. A really clever strategy. We've had a lot of information here, but let's look at the big picture. Okay, bacteria, these are things that are not viruses. They're organisms that have cells, but they have no nucleus. There's ancient ones, the archaea, and there's the more widespread modern ones, the bacteria. Cell wall made of peptidoglycan. And this is important because, well, we'll get to that. Anatomy, that's the shape. Are they coccus, round, bacillus, rod shape, spirali? Oh, or what about colony morphology? You see, a lot of these features help us to identify the bacteria. You have someone sick, and you can't just say, well, I think you have such and such. You have to very methodically look at all the bacterial features. So you have to look at the kind of colony it forms. You have to look at the thickness of the wall through a gram stain. Is it thick? Gram positive? Is it thin? Gram negative? Does it have a capsule? That's slippery polysaccharide. If so, then we have problems, especially if it's in the respiratory tract. We're looking at strep pyogenes, maybe pneumonia. Glycocalyx, that slime layer, we think of mutans. And look at that name, Streptococcus mutans. Okay, it's always mutating. So we always have to brush our teeth. We can't just like rinse with Listerine or something. We have to floss and brush before the bacteria forms a plaque and then segues into periodontal disease. Endospores, these are proteins released by the cell wall. That's what the peptidoglycan is about. Exotoxins, we think of the Clostridiae group. Botulinum, where you relax to death. Tetani, where you kind of flex to death. Difficile, where you have diarrhea to death, I suppose. How does bacteria move? Does it have a flagella? If so, we look at something scary like cholera. Generation time, the champion, E. coli. How fast can you reproduce? That's the generation time. Finally, pili. These are anchoring devices, but they're also used for transferring genes. But scientists have found ways to block the pili in cases such as gonorrhea. This is a scary bunch, but there's some good ones out there too. It's not all gloom and doom when it comes to bacteria.